vapor pressure colligative property and relative lowering of vapor pressure. Unit solution. Let us start with first question. What is vapor pressure of a liquid? Answer is at constant temperature and in equilibrium state, the pressure exerted by vapor over the surface of liquid is called its vapor pressure. Let us explain by making a figure. Suppose we have taken a sample of water in a vessel and the vessel is covered or sealed. So the volume over the liquid is fixed. It is water sample. Now temperature is kept constant. That means the vessel is in room temperature. What will happen? Gradually, molecules of water started to escape from the surface into vapor stage, even without heating the sample. Okay, molecules from the surface of liquid started to escape into vapor stage. The process is evaporation. Liquid started to move into vapor stage. This is evaporation. It is rate of forward reaction. But after some time, when the space over the liquid containing larger number of vapor molecules, then some of the vapor molecules come closer to the surface of liquid, and then reverse reaction, that means condensation is started. So now there are two opposite rates are going on, rate of evaporation and rate of condensation. Rate of condensation, backward reaction, but still the forward rate is faster. So more and more number of H2O vapor, H2O molecules in vapor coming, and there will be a time when rate of forward reaction will be equal to rate of backward reaction. That means equilibrium established. At this equilibrium, at constant temperature, whatever is the pressure exerted by vapor over the surface of liquid, that pressure is called vapor pressure. Vapor pressure. This is, suppose, PA naught. So vapor pressure exerted by vapor over the surface of liquid, pure liquid. Therefore, it is said that in equilibrium state at constant temperature, the pressure exerted by the vapor over the surface of liquid is called vapor pressure. Now, let us move to the second topic. What are the factors? Factors affecting vapor pressure. There are three factors. There are three factors which affects the vapor pressure. Number one, temperature. Number two, nature of liquid or intermolecular force among the molecules of liquid. And third one is presence of non-volatile solute, of non-volatile solute. Let us discuss one by one. Temperature. As we know, as the temperature increases, kinetic energy among the molecules increases, intermolecular force of attraction getting weaker and weaker, and evaporation increases. So the temperature directly affect the vapor pressure. Vapor pressure is directly proportional to the temperature. Larger or at higher temperature, a liquid has higher vapor pressure. Now, second point, nature of liquid. Here, nature will be decided by intermolecular force of attraction. That means intermolecular force of attraction among molecules of a liquid determines the volatility of a liquid. A liquid in which intermolecular force intermolecular force of attraction is weak, has higher volatility. Let us take example. Intermolecular forces among molecules of compounds decreases as the intermolecular force is strongest in glycerol, and then it is weaker from glycerol into water, and still weaker in case of ether. Therefore, vapor pressure of these liquid increases from glycerol to water to ether. That means vapor pressure in ether is highest. Now take third point, that is presence of non-volatile solute. Presence of non-volatile solute in solution. This is very important point. A non-volatile solute occupies some space some space at the surface of liquid, and thus reduces escaping of molecules of solvent from the surface into vapor stage. This causes decrease of vapor pressure of solution. Let me figure out these two cases. If you are taking a pure sample of water and covering it to make the volume over the surface of liquid constant or fixed, the molecules in pure liquid are only the molecules of solvent, that means molecules of pure liquid. There is no impurity into it. There is no hurdle or any particle which can resist the escaping of molecule. As a result, molecules can easily escape from the surface of liquid. And finally, in equilibrium state at constant temperature, the vapor pressure, whatever it will be, is vapor pressure of liquid. Suppose the vapor pressure is Pa naught. Now take another example, a sample of water in which small amount of sugar, is also present. Sugar molecules are not volatile. They do not escape from the surface, and at the same time occupy some space at the surface. Suppose these hard balls are sugar molecules. So what will happen? These hard balls occupy some space at the surface and reduces the evaporation of water molecule over the surface of liquid, reduces the escape of water molecule into the vapor. As a result, the vapor pressure of solution is reduced at the same temperature and in equilibrium state. This is sugar molecules and this one is water molecule or H2O molecules. So now you can understand why the vapor pressure of solution is less than vapor pressure of pure liquid. Vapor pressure of solution is lower than the vapor pressure of pure liquid. Draw a graph. Let me draw a graph for the two solutions. One, the pure solvent, and another is solution. X-axis shows increasing temperature Suppose 0, 10, 20, 30, 40, 50, etc. degree Celsius. Here is vapor pressure. The pressure rises up 10, 20, 30, 40, 50 and so on 60. So this one is vapor pressure. Pressure increases upside. Now for pure solvent, the vapor pressure should be like this. With increasing temperature, vapor pressure increases. But for the solution, it should be like this. So here is solution and this one is pure solvent. Solvent. You will find the vapor pressure decreases. Here vapor pressure decreases. So there is a decrease in vapor pressure. This is vapor pressure of solution. Next, consequences of lowering of vapor pressure. What happens? Due to presence of a non-volatile solute in solution, the vapor pressure of solution reduced in comparison to vapor pressure of pure solvent or pure liquid. This in fact led to the concept of colligative property. Colligative properties. Now next question is, what are colligative property? What are colligative properties? Definition of colligative property will be given as the properties of the properties of a dilute solution containing a non-volatile solute depending non-volatile solute Properties of a dilute solution which are depending on the number of solute particles in solution and not depending on the nature of solute are called colligative properties. What are these colligative properties? So there are 4 colligative properties. These are: number 1, relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and at last osmotic pressure. These 4 are colligative property. That means these 4 are such property of a dilute solution which only depend on the number of solute particles present in the solution, not on the nature or properties of solute particles, not on the properties of solute in the solution. Whether we are taking 1 mole sugar or 1 mole urea or 1 mole glucose, these 4 properties will be same until we are taking same number of mole of the solute. Of course, there is a exception. If there is dissociation or association of solute in solution, then property expected differ from that observed. So these are the colligative property. Now I am going to discuss one of the colligative property, that is relative lowering of vapor pressure. Relative lowering of vapor pressure. In short, it should be written as RLVP. So, relative lowering of vapor pressure. Here, we will derive an equation for relative lowering of vapor pressure from Raoult's law. Suppose a solution containing a solvent, volatile solvent containing solvent which is volatile solvent A and solute non-volatile B. Suppose mole fraction of solvent in solution is XA, mole fraction of solute is XB. Suppose at same temperature, vapor pressure of pure solvent is equal to PA naught, and vapor pressure of solution containing non-volatile solute is PS. Now, according to Raoult's law, Raoult's law, PS is directly proportional to XA, or PS is equal to PA naught into XA. This is the formula on the basis of Raoult's law. We know XA and XB, that means mole fraction of all the component in solution is equal to 1, or XA is equal to 1 minus XB. Then from equation 1 and 2 we may write, from equation 1 and 2 we have PS is equal to PA naught into 1 minus XB, or PS is equal to PA naught minus PA naught into XB. So the formula finally comes PA naught minus PS by PA naught, relative lowering of vapor pressure, is equal to XB. This is final equation. It says relative lowering of vapor pressure is equal to mole fraction of solute, where PA naught minus PS is equal to lowering of vapor pressure, and PA naught minus PS by PA naught is called relative lowering of vapor pressure. Now let us discuss the real life application of relative lowering of vapor pressure. Real life applications of relative lowering of vapor pressure. Here I shall discuss two important real life example. Preservation of food, preservation of food. When large amount of sugar or salt are added to food, the vapor pressure of water decreases. Because of this, water molecules become less available for microorganisms and microbes cannot grow easily. For example, fruit juice, jelly, pickles, salted fish, or meat are preserved. These are due to lowering of vapor pressure. Thus, relative lowering of vapor pressure helps in food preservation. Take another example. That one's humectant in cosmetic and medicines. Substances like glycerol or polythene, propylene glycol. Once again, I am telling it. Substances like glycerol or propylene glycerol are added in face creams, toothpaste, and moisturizers. These substances lower the vapor pressure of water, preventing the water from evaporating quickly. Therefore, products remaining moist for a long time. So, humectant, humectants in cosmetics, or in medicine. Therefore, products remain moist for a long time. In this, now finally, I have come to the end of this video. In this video, we understood the concept of vapor pressure, the idea of colligative properties, and the relative lowering of vapor pressure, along with their fascinating real life applications. But chemistry does not stop here. Two more very powerful colligative properties are waiting for us: elevation of boiling point, depression of freezing point. These will be discussed in my next video. These are not just textbook formula, they play an essential role in plants surviving in cold climates. The fascination of human body, anti-freezing in car radiator, and many other biological and environmental system. So, in the next video, we will uncover how simply adding a small amount of solute can rise the boiling point, lower the freezing point, and completely change